Right, so today I take a look at an introduction to related rate. Kindly subscribe to the channel so we can continue to make maths beautiful. So I'll introduce this concept with series of examples. Then we will run through ways to solve or ways to relate their rate of change. It's quite easy. Let's take the first example. It says an ice cube. Of course, there are always keywords. It's a cube, which means we are expecting to see equal sides. If this is S, the sides will be that equal. So if it is a cube, then I can say the volume is just S times S times S, which is x to the power 3. What do I need to do? I need to relate the volumes rate. Volumes rate means I'm going to look for dV dt. So I can use my concept of chain rule to drive an expression for dV dt from dV ds, because v is a function of s. So I can find dV dx and multiply by ds dt. So if I look at v equals x to the power 3, then my dV ds is 3x squared, which means my dV dt is just 3s squared times whatever ds dt was. Because it said the ice cube is melting, it means my side is not a constant. It will continue to decrease. So this is not a constant. So ds dt is not 0. So we can solve this, or if we are given that, we can solve this expression. But we are only supposed to relate them, so we can stop here. Take a look at the second example. It says the width and length of a rectangle are increasing. It's a rectangle. The width and length are increasing, so neither of them are constant, so we can derive them. Is that okay? We can derive them. We have to relate the rate of change of the width and the rate of change of the length with the area. So what is the area of the rectangle? It is the width times the length. This is a product. So we could just look at the product rule. Hold 1, derive 1. So my dA dt, I hold W, derive L, I have dL dt. Plus hold L, derive W, dW dt. This is how they are related. Then with enough information, we can solve the rate of change of the area with respect to the width and the length. I'll take the third and fourth examples, and let's get the concept through together. 1 minute. Third and fourth. The third one says it's a sphere. So a spherical balloon is expanding. If the sphere is expanding, what that means is the radius is not a constant. The radius keeps increasing. So it's expanding means we can look at the r dt, and it's not a 0. It says we should relate the rate of change of the surface area. So we need to know the surface area of a sphere. Surface area of a sphere. A is just pi r squared times, A is 4 pi r squared, yeah, of sphere. We have A is 4 pi r squared. So we need to relate the rate of change of the surface area. So I'm going to look for dA dt. dA dt can come from dA dr times by dr dt. It looks like this is going to cancel that. Then we have our dA dt. We didn't change anything. So if from the surface area I can find dA dr from this is just 8 pi r. So this 8 pi r, yeah. So my dA dt is just 8 pi r times by my dr dt. So with enough information, then we can, if we know dr dt, then we can sub and then find the rate of increase of the area. Let's take a look at the fourth example. So the water in a cylindrical tank is dropping. So if it's a cylinder filled with water and the water keeps dropping, it means that height of the water is not a constant. So we can find the h dt. It's not a constant means it's not going to be a zero. But what will be a constant is the radius. The radius of the cylinder will never change. So that will be a constant. Let's see how this affects, how they're related. The water in the tank is dropping. Relate the rate of change of the water level to the volume of the water. So we need to know the volume of the cylinder. Volume of the cylinder V is pi r squared times height. This is a product of my r and h. So if I need the V dt, again I can use the product rule. Hold r, differentiate h, hold h, differentiate r. Of course pi is just a constant. So if I hold h, I have 2r pi h, then dr dt plus. Now I'll hold the r squared and differentiate h. I have pi r squared dh dt. Product rule. But it says that the water in the tank keeps dropping, so the height is not a constant. So this is valid. But the radius of the cylinder is a constant. What that means is the r dt will go to 0 because the radius is a constant. When you derive a constant, it's always 0. So if this is 0, then everything here goes to 0. And what that means is my dV dt is just pi r squared times with dh dt. So in this video, I'm only introducing the concept. In the next video, we will pick examples and then we will solve related rate problems. Do subscribe and check out for the next video on related rate. Thank you.